Now, if we want to solve a system of equations, well, of course, we need to define what the system of equations even is. But if we want to solve the idea of two or more linear equations involving the same variables, well, wait a second. If we say have, x plus y equals 1, x minus y equals 0, or something similar, then we can do one of two things. One, we can add them together. That's called elimination, and we'll discuss it later. Or, alternatively, what else can we do? Well, we can express x equals y. So we label this 1 and this 2. So from 2, x equals y, substitute into 1. And this would give us, well, 2x equals 1, x equals 0.5, or 1/2. And y equals x equals 1/2. Now, when we solve a linear equation, what are we actually finding? Well, here it says, an ordered pair of numbers. Why an ordered pair? Well, suppose you have the variables a, x, and y in your particular set of equations. Or a, b, c, d, e, f, g, and so on, all the way to y, or z, or z, depending on regional pronunciation. So, you can have the whole alphabet, but when you list them, the results you get, you will list them in some order. This order determines what the number you actually get is. Well, the numbers. So here, on an xy plot, an ordered pair would be x, comma, y. And if it was three-dimensional, then that would be x, y, and z. Or z. Oddly, when I went to the US for university, I was continuously saying z, but when I was in Canada for high school, I kept on saying z. So, I guess I just wasn't up to times. Now, funny stuff aside, these are some of the situations you can get when you have two linear equations. Now, you can have one solution, in which case they intersect at one and only one point. This is for a two-dimensional plot. So you only have two variables, a and b, c and f, x and y, whatever you want to call them. So you can have these two variables, when plotted, only intersect at one point, in which case we call this consistent and independent. Consistent being at least one solution exists. So to have these two equations both be true is real. It is realistic. It is not impossible. Now here, when we have infinitely many solutions, the two lines overlap completely. Now I'm pretty sure we all know why the no solutions choice is that they are parallel. Because we know that parallels don't cross, right? Parallel lines? Yeah, there's a little problem with this. If we add more dimensions, there is the issue of lines that are skewed. As in, think of a three-dimensional line going like this, and another three-dimensional line going like this. Well, they never cross, but they're not parallel. As you add more dimensions, it gets more complicated, but for now, why is this inconsistent? It means that, whatever your number 1 is and number 2, this is impossible. For both to be true at once. That's why we call it inconsistent, because it's inconsistent with the idea that you can group these two linear relations together and claim that, well, there is an answer to be evaluated. Whereas here, with infinitely many solutions, if they're the same line, of course, they completely overlap. They have infinitely many points at which these two lines both are true, and thus we call this consistent because there is at least one solution. It is possible for these lines to both be true, but it is dependent. It is not independent because these two lines match up at every single point. So at every single point they can be thought of as, well, kind of depending on each other. Whereas in the independent case, this line goes this way, that line goes that way, sure, they cross. But do they actually dictate each other? No. Substitution is used when the coefficients in a system are not equal. So if you have x plus y, x minus y, then you can feel free to just add the two together and get 2x equals some constant. Or some other relation, say z. So, use substitution to solve each system of equations. Now, example 1, this is a very big example. Now, y equals 3x, 2y minus x equals 6. Convention will usually draw these brace brackets, but convention, when they give you the problem, may not have these numbers. It is very possible that they won't. I do point out that in many textbooks you don't see the brace brackets either. Why? Because the textbook writing people are lazy. And honestly, the reason why we didn't include brace brackets to begin with was because we need to make this very clear that very often in textbooks you can only define the boundaries of a problem, like a set of these equations, by looking at, say, A, whatever, whatever, B, whatever, whatever. And of course, it's common sense with the columns, but that's not the point. So, here we have 1. Y equals 3x. We substitute this in sub 1. Convention has it that you will write these steps using, well, as few words as is reasonable, but still enough to communicate what you have done. So, that is 2 times 3x minus x equals 6. So that's 6x minus x equals 6. I do realize that I'm pretty sure we can all multiply 2 by 3 and then subtract 1 all in one step. But, well, most teachers prefer that you show more steps than less, unless it gets excessively crowded, of course. But the point is that showing a few more steps generally reduces really dumb mistakes. So, here, 5x equals 6, we can write this as 1.2 or 6 over 5 if we so wish. Now, y equals 3x. This, depending on teacher preference, they may ask for you to write, oh, sub into 1. Of course, that would mean this needs to go on a separate row. But depending on how good your teacher thinks you are, back when I was in grade 9, my math teachers would let me get away with just writing this without this part. So depending on how good your teachers think you are, you may be able to get away with not doing so. So, at the end, you must, well, you really should at least, some teachers you must, present your solution. So we evaluate that x equals 1.2, y equals 3.6. This is how we present our solution. Of course, depending on area, you might have to write solution, this. Now, this one, y equals 3x minus 2, y equals 2x plus 3. sub 2 into 1 or 1 into 2 really doesn't matter here because both of them are y equals something. Three x minus 2 equals 2x plus 3. So that's x equals 5. And what do we do next? Well, then we writing extra steps doesn't hurt unless you're crowded. So sub into 2 and y equals 2 times 5 plus 3. So this is equal to, okay, yeah, whatever, 13. Now, does this make sense? We check our answer and it's, hey, 3x minus 2, 2x plus 3, okay, x is 5, fine. And 13, yep, that's correct. So, solution is x equals 5 and y equals 13. Now, yes, we did abbreviate some of the steps, but the most important step we have not abbreviated. And that is, depending on argument, either the substitution or the final answer. Did you know that in the Olympiads, you can get the majority of marks for a problem, even if you get the final answer wrong, by using the right formulas? Alright. 2y equals 6x minus 5, 4x minus y equals 9. So how do we get this to a point where it is possible to substitute? Well, so 2 4x minus y equals 9. 4x minus 9 equals y. Now, this can now be substituted into 1. So 2 times 4x minus 9 equals 6x minus 5. So that's 8x minus 18 equals 6x minus 5. And thus we have 2x equals 13. X equals 6.5. Alright, what is y? Well, we can choose to label this as 3 if you wish, or you can just say, oh, substitute this into 2 and be done. So we choose to, let's just sub into 2. Usually it's somewhat preferred to sub into the original problem because, well, there's less likelihood of doing something wrong in the middle. Or at least being affected too much by doing something wrong in the middle. So sub into 2, 4 times 6.5 minus y equals 9. So y equals, well, we know we move this over, we move the 9 over there. So 26 minus 9 and y equals 17. Now, what do we do if we find ourselves a little bit crowded for room and all that's left is a solution? We could start a new column using the standard dash line convention, or in this type of problem, when you are solving one of these, what do? Well, usually, you just go straight to the side. Equals 6.5 and y equals 17. Now, this is, of course, not the same as in problems where there are still more steps to come, in which case you do use the dashed line convention. Provided, of course, that your teachers allow it. Now, here we have of course, it's fine if you don't actually put this brace bracket, but for many people who are used to seeing it, it's a bit of a force of habit. Now, y minus 0.1x equals 0.25. That means 1 gives us y equals, technically we should put from 1. Y equals 0.25 plus 0.1x. So sub into 2, and that gives us 0.3x plus 0.25 plus 0.1x equals 2.25. So 0.4x equals 2 and x equals 5, and we sub this to 1, and this gives us y minus 0.1 times 5, and this is equal to 0.25. Y equals 0.75. Now, the solution here is then, well, I do point out that I, back in high school, never really used this solution thing because I just presented this at the end and that was it. But apparently many places do ask that you write, oh, solution is something, or solution something at least. So, guess we'll stick with it.